Hello, this is Tyler Cruzin, Haran Jitharanjan, and I'm Marty Tiss. We are Team 2, and this is our Battlefog Rube Goldberg Machine project, Spring into Action. In this report, we'll be going over how the target specifications were established, the identification of customer needs, the intellectual property search that we conducted, the prototypes that we designed and built, and along with the test results and recommendations that we came up with, and an economic analysis of our project. And here's Haran with our mission statement.
So here, as you can see, is our mission statement for our Rube Goldberg machine. So our product description here is a Rube Goldberg machine that teaches basic kinematic and energy concepts to 11th graders. And some of the benefits of our product, it's going to be a simple yet educational BRG machine, and it's an interactive kit that demonstrates basic principles of motion. So some of the assumptions and constraints we were given, the ping pong ball has to enter and exit at the same velocity. It has to be assembled on the pegboard that was given. It has to have 3 adjustable components and an Arduino component, and it has to be easily stored. And some of our important stakeholders is VTEPs, Inc., and distributors and marketing. And now Marty will talk about our customer profile.
This is the customer profile for Julie Tiss, who is a Fairfax County public school teacher in Fairfax County. We believe that she would be a good customer to sell our product to, because she would be able to use our product to introduce and show to her students the basics of physics, including conservation, momentum, and energy transfer. Our target, the students that we are targeting with this project are primarily 11th grade physics students. We chose this grade because in 11th grade it's often when students really begin to go deep into the physics, the topic of physics. The topics that we wanted to cover in our project were conservation of momentum and the changes in energy that can occur. And here's Tyler with our customer needs information.
So this is our customer needs table, and as you can see on the left are a list of customer needs. They include easily assembled, easily stored, lightweight, runs on battery, demonstration of kinetic energy. And from these we were able to create a list of engineering characteristics, such as the mass, the size, the number of parts, and so on. And from this table we were then able to create this, the target specifications table, which lists in order of importance, based on the previous table, which things that we need to focus on most. And as you can see, at the top is the focus on energy and the amount of energy left at the end of demo. And as you'll see later in our presentation, both of which were accomplished with our final working prototype. And next is the intellectual property search. And this patent is actually a patent for the stop in a lacrosse stick head. And this was used in our Station 1 to stop the ball as it comes in with a speed of 3.4 miles an hour. And we needed to quickly stop that ball. And so we took ideas from this to put into our final prototype. And now next is Haran to talk about Station 1.
So here we have 3 CAD models for our ideas for Station 1. And here we have a concept combination table for Station 1, which basically illustrates the different components of our following ideas. So essentially for Station 1, we'll have the ball entering at the given velocity from the entrance ramp, and then stop by a cupping mechanism, as Tyler mentioned. And then we will have a lever which is controlled by a servo motor, which is also controlled by an Arduino, that will kick the ball up the incline plane and take it to our next station. And the idea that we chose for this station is Design 3, as the design was very intricate, and it had the side railings that helped ensure that the ball would stay on path. And now we have our ideas for Station 2. So in Station 2, the ball will come from the incline ramp and fall into this platform, as Design 3 has, and then fall into that hole, which will take it into the spring station. But some of them also, we just had the ball drop from the incline ramp into the station. So in Station 2, the spring will initially be decompressed, and once the ball is landed, the spring will decompress and shoot the ball into our following station. And we chose Design 4 for the station because it had side railings like the previous one that ensured the ball would stay on path and its simplicity. And finally, we have station 3. So the ping pong ball that was shot by the spring will enter the station and essentially complete a loop-de-loop as you see here, and this will demonstrate conservation of energy. And now Marty will talk about the prototype the team has developed.
Here is a CAD model of the prototype that we designed and built. The first part of the model shows a pendulum swing, which will be triggered by the Arduino servo motor right here. The pendulum will hit the ping pong ball up the ramp, which will then dislodge this marble, which is sitting on the edge of this platform. The marble will then dislodge a pencil that was holding a spring. The spring will then launch this small marble into this large marble right here, which will dislodge this pencil and release that ramp. The ping pong ball will then roll down this ramp and off the BOG machine. This prototype was made primarily out of cardboard and duct tape with some pencils used to help support the machine as they are more rigid than cardboard. We also used a spring and a couple of marbles to help have our machine go through the project. The adjustability that we have in our project is that the first ramp will be able to be adjusted different sizes, so the students will have to calculate the size that they need in order to be able to get the ping pong ball up the ramp. And then the spring can be interchanged with different types of springs, so the students will have to calculate how much power they need to launch the marble. And then the second marble, the size of the second marble will be adjustable, so the students will have to calculate the amount of momentum they need and calculate the mass of the marble they need, so in order to keep the conservation of momentum. And here is Tyler with discussion of our test results.
Before I get into discussion of test results, I just want to highlight the 3 key points that we were talking about. For the pendulum swinging down and hitting the ball up the ramp, that demonstrates a change from kinetic energy up to potential energy. When the marble drops and releases the spring, it is a demonstration of Hooke's law and elastic potential energy. And when the marble collides with the bigger marble, it is a demonstration of conservation of momentum. And now into our test results. From the test results, we learned that we had a unique look to our machine. Not many other machines had a look that was similar to ours at all. Also, we never saw a station that was the same as ours. So our machine contained original stations. However, we did notice that we needed to improve the consistency, as our machine was not always working properly, and sometimes the transitions between the stations failed. And so, moving forward, that's what we decided that we need to improve. We need to improve the consistency and make sure each station works properly each time. And we need to test less sensitive transitions, as most of the transitions between each station are very fragile, and so the littlest movements can set them off. And so that was where one of our failures was. And now up next is Haran to talk about economics.
So here we have an economic projection of our Rube Goldberg machine. So we projected that the 2 break-even points for our project will be at 55 cases sold and about 102 cases sold. So ideally we're trying to sell around 78 cases sold, because that will maximize our profit at around $2,000. And yeah, and now we'll look at a cash flow diagram of our project. As you can see here, all of our present worth, future worth, annual worth, and IRR value suggest that this project is will be a positive investment, and the payback quarters is projected to be at year 3, quarter 4. And now we have the assembly time worksheet, which essentially shows the estimations for purchasing the materials or components we need for our project. And essentially from this table we can get the manufacturing and assembly costs, and we'll look towards exploring other materials to be used in order to minimize our manufacturing costs, but also we have to keep into consideration that the impact of manufacturing costs on our overall product quality, as that's what's most important. And now Tyler will conclude our presentation.
So, in conclusion, our target market is 11th grade physics students, as we're teaching basic physics concepts. And we also were able to build a successful prototype. While there still were some errors, it was a successful prototype. We did get it to work. And some of those errors were the consistency in each station, which we decide needs some more improvement, and the transitions between those stations, which need some improvement as they're fragile. And also, through all of our economic analysis, we decided that this project is in fact economically profitable and should be moved forward and invested in. And that is the conclusion of our presentation. Thank you very much for watching.